constant velocity. The purpose of this lab was to explore how real-world examples of constant velocity compare to computational models. Constant velocity is achieved when the net force of an object is zero. To accomplish this, we attempted to recreate an environment with a net force of zero and observe the motion of an object in this space over multiple time intervals to see if constant velocity was achieved. Then we set up a computational model of the same interaction to see the differences in the scenarios. We found that the computational model had a true constant velocity, whereas our real-world example was close but had slight differences in velocities over each time interval. In reality, the only times the net force on an object could be zero is in a vacuum or when the object is at rest, but we still needed to create an environment as similar to a net zero force environment as possible. To do this, we used a water bottle rolling across a whiteboard. The force of friction and air resistance were the only two forces that would be responsible for eliminating this constant velocity, so we minimized them as much as possible by using a rolling object and a smooth surface. As seen in the diagram, the normal force and gravitational force are equal to each other, so the net force in the y direction is equal to zero. After our initial push, there is no net force in the negative x direction, or to the left, and slight friction force to the right. Therefore, there is only a constant velocity in the negative x direction. However, the direction we chose was arbitrary because we could have flipped the video so that the water bottle was traveling from the left side of the screen to the right side of the screen, and therefore our velocity would end up being positive 0.21 in the x direction rather than negative 0.21 in the x direction. Due to this being at such a small scale and a short time, we can assume that friction has no effect for tracking purposes. The image on the right shows this tracker program after we tracked 30 intervals of the object's motion. The purple lines show the coordinate plane we constructed for this object, with the origin being at their intersection at the center of mass where the object began. The blue line corresponds to the diameter of the bottom of the water bottle. This diameter was used as a basis for the program to be able to judge distance. Each red diamond is a point that I manually placed that has an equal time interval between each point. Data from the tracker plots position on the y-axis and time on the x-axis. With this, we can see a noticeable linear trend. On a position versus time graph like this one, a line indicates a constant velocity, and in this graph specifically, we see that an almost perfectly straight line. However, it is not perfectly straight, and this could be due to a number of reasons. First of all, human error could have contributed to this, as we manually placed each updated interval at the point that we assumed was the center of mass, but even if we were just slightly off, the small scale of this experiment shows this mishap in the graph. Another reason could be due to the fact that a zero net force environment is impossible to create in our circumstances, and there was a slight force acting on our water bottle. Next, we compared this data with a computational model of a similar scenario. To do this, we created a line of best fit through the points found in the tracker and used the slope of this line as the constant velocity in the computational model. We then wrote code that would take this velocity and apply it to an object starting at the origin by updating its position during the same time interval as our water bottle experiment. The graph on the right shows this data, and we can observe that velocity is truly constant in this computational model rather than the slight variations in our original model. As discussed before, achieving a true net zero force is almost impossible in reality and only really viable in these computer models. In terms of how many forces are acting upon this water bottle to create a net force of zero, we would first need to isolate the water bottle at a specific time. Then we would need to classify the types of forces, and then we would need to assume a net zero force. Finally, and we could brainstorm the amount of forces. In this case, we know gravity and the normal force are acting upon the water bottle, as well as friction and air resistance, so that's 4. But to achieve a net zero force, there must be another force in the x direction that is equal and opposite to the force of air resistance and the force of friction. However, the number of forces in either negative or positive x direction depends on whether or not we classify air resistance and friction as two different forces, or if there are multiple other forces equal and opposite to the air resistance and friction. Therefore, it would not be possible to say how many forces are added together unless we make certain assumptions. In conclusion, we found stark similarities in our observations and the computational model, suggesting that not only can the computational model predict our observations, our experiment itself was highly accurate, and a net zero force was practically achieved.